Hey guys, welcome back to Chris V's RF Designs. So in this video I've made some improvement from my last video of finding the input impedance of at the RF port of the double balanced mixer using the diodes HSMS 28 there should be an X here. I used the 9 here. I'm going to be using the 2829 crossover quad. That way we can make sure that our lines are not going to cross over each other, because we're using transmission lines instead of using transformers. Transformers use the coils, and using a transmission line uses two lines that are parallel to each other. It literally looks the same, as you can see here. Instead of our transformers that we used from our last video, we used the 3-winding transformer at the input of the oscillator, and also at the input of the RF input of the input RF port of the double balance mixer up here also. So this is literally the same thing as a center tap transformer. Instead it uses transmission line instead, because if we're using inductance from my last video I told you that maybe you shouldn't be using the 3 mutual inductors, but I'm wrong. It will work. It's just that the inductance was wrong. It was not matched correctly with the core diodes here. So that was the only problem. And also from the last video, the current probe was going in the wrong direction, and therefore I had the wrong input impedance. It was negative, and instead it should have been positive, and we got so it should have been positive instead. Okay, so in the transmission lines here, we need to make sure we include FR4, whatever board we're using for our substrate, and I put our substrate values here. You can also look up from my last videos of designing low noise amplifiers how you would find these values and put them in, but you can go back there if you want to know how to do that. But let's keep on going here. So this is basically a Marchant ballad. It's something made by that person, Marchant, I believe, and so you just basically so you can see here I created the layout of how it would look like on a circuit board. So I found, this right here is the diode bridge. And here, HSMS 2829, I found the pads. You can see right here, this is an SOT 143, I think. Yeah, right, 143. And you would find the pads either here or some other place. They have the pad lengths and everything. And I came up with these sizes for the pads. It should be right here, these pin sizes here. They have the recommended pad size somewhere else. Also, you can look it up, SOT 143 pad sizes, and they'll give you a recommended size for them. And you would recreate it, put them in Eagle PCB, and how far apart they are. I'm not going to show you exactly how I did it here because there's a lot to do to show you how I put the pads there, but that's that. And so this is basically the March and Ballon, as I said here. This is the right here. This is the March and Ballon. It is basically a transformer, center tap transformer that goes through these two sets here, which goes where it should be in a bridge rectifier for the double balance mixer. And then down here, so I have literally same thing. It is literally kind of like how this should be working, but since we have an IF output that's center tapped, that's coming from the output here, there's no way for me to create the circuit so that, you know, I can bypass this wire without, you know, having to bypass this spot here. So what I did is that I had the top layer here go to a via, and via down to the bottom, and make this as a small transmission line, as I show up here. So as you can see, these are ends, and then they end into these coils. These coils actually, the inductance actually is represented because of the vias here. So the vias are the inductors, and this is just an extra line that I put in there. I don't know if I should have just go ahead and put another inductance in there instead of a transmission line. I don't know if that would make a difference, because it's a small line, and I don't think it's going to make much of a difference. It's 1.46 millimeters long, and comparing that to, you know, how much you need to make sure that this is small compared to the transformer, to the sizes of the the size of the quarter wave transformer. So that is the reason why you see that this basically the center tap transformer at the RF port at the RF input, and also the taking that center tap as the IF output. We needed to make sure that this line is going around here instead, or going in this direction instead of this way. I could have probably actually made this in a different way, where the IF output here, I could have had it going in between this transistor, underneath the diode bridge, cross quad maybe. Let me know if you guys figure out if I should do that or not, but for now this is the way that I'm going to be doing it, my way. And so I decided, well, it shouldn't be too bad with a small bypass here, and everything else grounded below here. So this is the IF, this is going to be the RF input, and right here is basically the transmission line that I put in here also. Down here, this is the transmission line. Stub match that I made here. That's exactly, so this right here is 11.2 millimeters long, right here, and then right here is 15.79 millimeters long. And I found that, so instead of having to find the input impedance to the RF port of the double balanced mixer, sometimes it's nice that you could just go ahead and play with the numbers, because it's might be even quicker, and not having to go through figuring all this out on a Smith chart and stuff. Just get the values, I guess, somehow. When this software is nice because you can also use a tuner and tune the width, or actually, so I would be tuning the length and the length of each of the stubs. The width needs to stay the same, and the FR4 should all stay the same, because that depends on how your characteristic impedance is going to be, but not your length. The length is what frequency you're going to be using. So you can vary these, MS12 and MS14 here. You can vary these. And down here in ZRF it will change. And I made it so that I could find somewhere where I could get 50 ohms and have very small amount of reactance right here. So that gives us a good match for the RF input match to our double balance mixer here, and giving us a good signal quality at 2.4 gigahertz here, with having less amount of harmonics coming from our fundamental, which is 2.4 gigahertz. And then, so from our last video, I didn't have a coil here and a capacitor here. This is a basically it's a low pass filter, I think. So if I exit this out, make this just a wire going through, and then exit this out, we have our frequency is going to be at our output of the IF. The IF output is going to be looking at as an output of right here it shows 2.4 gigahertz. And we don't want that. We want to have 100 megahertz coming out at the IF. So as you can see here, we do have 100 megahertz here. It looks like it is coming out, but the thing is that we need to use a low pass filter to filter out the high frequencies and just be left with the frequency at 100 megahertz. So we need to make sure that our inductance and our capacitance, you could just go ahead and use the tuner also for that and find a good enough inductance and capacitance value that will suffice your circuit to get 100 megahertz output. And I don't know what else I need to include for you guys to know, but this is basically it. So as I said, as I did in my last video, I found the RF input impedance, but it is nicer if you just go ahead and use the tuner here, because it's just going to save you time from having to find a match circuit between it. You can find it by either, seeing that you have a high fundamental signal coming from at 2.4 gigahertz here in the harmonics, or seeing over here that your ZRF is going to be as close as possible to 50 ohms. And so that is And that's about it, guys. I will be connecting my low noise amplifier in this spot here. I might be making the low noise amplifier different from my last video by putting it series cascade of two amplifiers together, and then feeding it into the mixer. But I'll think about that, and or maybe I might go ahead and just cut this part off as the mixer, and then have SMAs here that will be I could connect them to my old low noise amplifier that I tested before and use that, or just recreate another low noise amplifier and connect that new one to this one. But I think maybe I could just go ahead and just connect. I just could draw out the transmission lines for the input and the output of the low noise amplifier here, and then I'll have this as my input to from the local oscillator at 2.3 gigahertz. I'll probably be using a network, I mean not a network analyzer, but a spectrum analyzer. And the spectrum analyzer has a signal generator on it, and I could use it at 2.3 gigahertz here, and then I can figure out what my output is at the output, and see what we get if we vary the voltage of the input of our low noise amplifier. You can see how much room I have for different voltage levels at 100 megahertz at the output. Therefore, that can be recreated as the message. We can recreate the message from 100 megahertz instead of 2.4, but I will be testing it hopefully later on when I get it manufactured. Let me know what you guys think about everything, but I'm going to go ahead and start putting the low noise amplifier in here, the old one that I had before probably, or actually I might be designing a new one and putting it in. But that's about it, guys. Well, that's just an update. Just want to show you what I've been doing through the process of designing a radio frequency integrated circuit design. So hope you guys liked my video, and please subscribe. Thank you. Bye.